I'm happy to kind of go through and do a couple if you are so inclined. Yeah, Lexi? Yeah, you can ask a question. No big deal.
Number
20?
yes.
Okay. So this says we have tan squared x is equal to 1/3. Everybody okay here? That's the problem, right?
Yeah.
Okay. So first thing I'd want to do is try to get the tangent of x by itself. So I have to cancel out that squared.
Okay.
How do I cancel out a squared? Yeah, we'll take the square root of both sides. Now when we take the square root of both sides, the square root cancels the squareds. Because we're doing it to both sides of an equation, we create a plus or minus, right?
Yeah.
And that's going to give me really 1 over the square root of 3. Because when I square root a fraction, I square root the top, and then I square root the bottom, and the square root of 1 is just 1, so I'll write it like that. So that is going to break into 2 separate equations. So that's going to be tan x equals positive 1 over square root of 3, and tan x equals negative 1 over square root of 3. And if you wanted to, you can rationalize the denominator. But since this is not a final answer, I'm not going to worry about doing it here, because I'm interested in the value for x, not what tangent's equal to. So I'm not going to bother rationalizing. It's just kind of, because it's not a final answer, I don't need to worry about it, kind of thing. Okay? All right. So now that I've got this, it's time to take the tan inverse of both sides to get the x by itself. And then we go to the unit circle. So how do I find where tangent is equal to 1 over the square root of 3 on the unit circle? How do I find tangents on the unit circle? Yeah, so remember that tangent is y over x. So here what I'm going to do is I'm going to look for a place where the x coordinate has a square root of 3 in it. No, it's just kind of harder to see what you're looking for on the unit circle if you've done that. So, okay. So if I do that, I notice that I see square roots of 3 in the x coordinate of pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. If I'm looking at my unit circle, which if you have that out and looking at, might be a good idea for these problems so you can kind of follow along with what I'm doing. Everybody see those 4 places where I see a square root of 3 in the x coordinate? Okay. So I know that tangent is positive in the first quadrant and in the third quadrant. So that's pi over 6 and 7 pi over 6. And tangent's negative in the second and fourth quadrants. So that's 5 pi over 6 and 11 pi over 6. So this is going to be my answer for part A, or those 4 values. Everybody good with that? Okay. For part B, we want our answers over the entire real line. So I could do this and just tack on a plus 2 pi k to the end of each of these answers, right? That's what we've usually done. But we could do a little bit better in this particular situation. So if I look at these two answers, and if I look at these two answers, how far are those apart? They are pi units apart. Right? If I do 7 pi over 6 minus 1 pi over 6, I get 6 pi over 6, which is just 1 pi. So what this looks like on the unit circle then, I'd have like one answer here and one answer here, or this distance is pi. So how far is this distance going to be? Also has to be pi, right? So because these two answers are pi units apart, I can condense this down into one infinite solution. So instead of saying I get this answer every 2 pi units and then this answer every 2 pi units, I can just get one of the two answers every pi units. So if I add pi to pi over 6, I get 7 pi over 6. If I add pi again, I would get 13 pi over 6, which is the one coterminal to pi over 6. If I add pi again, I'll get the one coterminal to 5 pi over 6. So it just allows me to combine those two answers into one answer. Do you have to do that? No, but it's like reducing a fraction. You wouldn't see a final answer in an answer key or a multiple choice test or something like that where we didn't condense those two answers into one, but it's not incorrect if you leave both answers. Notice we could do the same thing here. And again, this is for k's, or integer values of k. Are we okay with part B on what I did there? More often than not, when you're dealing with tangents, you can condense your two answers into one if you have a plus or minus, like we did here. Right? When we solved this, we got the plus or minus. And even sometimes when you don't have a plus or minus, you can do this for tangents. For sines and cosines, if you have a plus or minus, sometimes you can do this. And even sometimes when you don't have a plus or minus, there's some rare occasions when you have like a quadrantal angle, an angle that lies on either the x or y axis. You can do that, but they're not very common. Tangents is really the one where you have to be kind of careful about. So for part C, we wanted the answers between negative 2 pi and positive 2 pi. Yes, Kendall? Sure.
So when you reduce them and then you added the pi, is that because the difference is pi, or you always add pi?
It's because in this particular case, the difference is pi between them, but it has to be the same difference both ways. Remember when I drew this picture?
Mm-hmm.
The difference this way has to be pi, and then also the difference that way has to be pi. So if you had a situation like this, where say this distance is 2/3, and then this distance is 4/3, you couldn't condense those two answers. They have to be pi each way for you to be able to do that condensing.
So adding the pi though is just because that's like the difference.
Yes, basically, yes. Mm-hmm. Okay. Good questions. All right. Am I okay to erase these little pictures I've scribbled on the side there? So, in part C, we're looking for all the answers on this interval. Well, we know part of this answer. We know these 4 answers from the previous part are good. Those are all of our answers from 0 to 2 pi, which is still going to cover part of that answer that we're looking for, right? Now what we need to do is figure out the answers between negative 2 pi and 0. How do I do that? Don't add. I subtract 2 pi from each of those 4 answers, right? So if I subtract 2 pi from pi over 6, I get negative 11 pi over 6. If I subtract it from 5 pi over 6, I get negative 7 pi over 6, and then negative 5 pi over 6, and then negative pi over 6. And that'll be my answer for part C. Everybody good with that one? And then my answer for part D is looking for things between pi and 4 pi. So I know that my answers for part A are going to be answers here, because 0 to 2 pi is still part of that interval, right? And then let's figure out the interval or the part from negative pi to 0. And we can do that using our answers from parts, or some of our answers from part C. We won't take all of them though. Which of these 4 answers are we going to use? Good, the negative pi over 6 and the negative 5 pi over 6, because those ones are greater than negative pi. The other ones are too small, right? Okay, so I'm going to write those 2 down on my list. And then the last part that I have to worry about is the part from 2 pi to 4 pi. How do I find those answers? Yeah, I'm going to add 2 pi to our answers from part A. So that's going to give me 13 pi over 6, 17 pi over 6, 19 pi over 6, and 23 pi over 6. And that's all of them. Lexi, are you happy with that? Sure. Did we go slow enough for you guys to kind of follow everything? I tried to be really purposeful and thorough doing that. I know that this is not always the easiest topics, so I want to make sure that I'm going at a pace that's easy to follow and keep up on. Kendall?
So for part B,
Mm-hmm.
do you know what the meaning for the X is telling you? Like, is that what you looked at? Or the last one, how did you know that that 2 pi is because that's it?
Okay. So if I look here, it's basically the same as this interval if I've just added 2 pi to each end. So that's why I've added 2 pi to each of these, because that'll make it the equivalent angles in the same interval. Does that?
Yeah, and then so the middle one, so you take that pi.
So what I did in the middle one is I used my negative answers from part C, and I just checked to see which ones are actually between negative pi and 0.
Okay.
So that was the last 2.
Okay.
The other ones were too small. They're smaller than negative pi. Does that feel okay? So I tried real hard on these to give you answers that like kind of overlap a little bit, that you can use your answers from one part to do the answers to the next part, because in practice, really what you're going to do is you're going to take your answers from 0 to 2 pi and use those to like build out as many more answers as you need, which I think is, like I tried to pick intervals where you got to do that, and maybe you had to be careful about which ones you picked, like in part D where we only need half of, the negative answers, or, Does that make sense, Kendall? Yeah, you're welcome. Okay. Should we do another, or you guys feel okay here? Okay, which one do you want to do? We're not leaving solving anytime soon, just FYI. We have a few more days doing this, right? But the solving problems will add a little bit of like more complication to some of them as we go. But we're not stopping doing solving today by any means. We're just going to continue, and the problems might get a little bit more complicated, but we're still doing the same process. And the only part that gets a little bit more complicated is the solving part, where we're getting the x by itself. And everything after that kind of stays the same, of how we used our previous answers to get the next part. That up part will all stay the same. So I don't know if you guys have some, let's maybe do one more from this assignment, and then we'll start talking about, the next step in the solving part, or the next kind of problem in the solving.
Yeah.
21. Sure. So 21 is definitely going to be easier than 20 was, for a couple of reasons. One, because it's not squared, and two, because it's a sine rather than a tangent. So it'll be easier to find those values on the unit circle when we go to look at them. So when I do this, I take the sine inverse of both sides to get sine inverse of 1/2 to get the x by itself. And then I'm going to go to the unit circle to find those x values. So what am I looking for on the unit circle? I'm looking for the places where y is 1/2. How many places should that be? 2. Because we don't want negative 1/2, we just want the positive 1/2. Good. So what are the two angles? Good. And good. That's our answer for part A. Really easy, right? Okay. For part B, I would just write the same thing, but I'll tack on that plus 2 pi k to the end. Is it possible to condense these two answers? No. Why not? Well, look at the distance between the two answers. It's not a full pi, right? It's 4/6 pi apart, so you can't condense them. That's it. That's all we can do. Can't get it any simpler than that. So that's it. That's our answer for part B, or those two. Okay with that? Okay. For C, we're looking for our answers on the interval negative 2 pi to 2 pi. So what answers do we know are there immediately? we know our answers from part A are going to be there because that's the solutions on the interval from 0 to 2 pi. And that's a subinterval of negative 2 pi to 2 pi, right? Okay. What part do we still have to worry about, though? The negative part. Okay. So to get those negative answers, what are we going to do? Minus 2 pi from each of the previous two answers. So the first answer is negative 7 pi over 6. That's correct. The second answer would be negative 13 pi over 6. Or, no, that's 11 pi. So I subtract 2 pi from that. So 2 pi is 12 pi over 6. 5 minus 12 is 7, or negative 7, excuse me. And then if I do the same thing, if I do 1 minus 12, I get negative 11. Okay with that? So just adding fractions or subtracting fractions. And if you need to use your calculator to kind of practice on that and double check yourself, it's okay to do that. You can use like the math frac command to do the subtracting fractions. Just leave the pi's off and the calculator will handle the fractions for you just fine. Right? You can do 1/6 minus 12/6 or just minus 2 and do the math frac command and it'll give you the fraction. Right? If you're not confident that you did those right. So that's our answer for part C. Let's move on to part B. So what answers do we know are there? Well, our answers from part A are always going to be in this interval because 0 to 2 pi is a subinterval from negative pi to 4 pi, right? That entire interval lies in there. So all of the answers from that interval lie there. Now let's look at the interval from negative pi to 0. Where do we go to look at those? We look at the negative answers from the previous and see if any of those are between negative pi and 0. Are either of those between there? No. So we don't have any answers on that part. There's nothing in there. Actually, let's just leave it blank. That's probably less confusing. And then we have to worry about the interval from 2 pi to 4 pi. So we'll do pi over 6 plus 2 pi. That gives me 13 pi over 6. That would be 17 pi over 6. Man, you need to work on adding fractions in your head, buddy. Okay, and that's it. That's all of our answers. That's everything for 21. I think this was. Yeah. So that one was a bit easier, right? Less to do, less answers to hunt down, right? Not so bad. And again, once you start getting good at these, like they go pretty quick, right? Because most of your answers for the next one are based on the previous answer, so you're really just working on manipulating and finding the right coterminal angles. Right? The hard part is getting part A, and once part A is done, that gives you all your answers, regardless of the interval that I asked for. You can get all those other answers just from looking at part A. The negative answers from the previous question. And since both of those guys are both less than negative 1 pi, we don't want either one of them. You're welcome. again, this part we look at A, this part we looked at C to figure out. This part we had to do on our own. The last part had to do on our own. Although we used, I guess we used our answers for part A to do that, but we didn't look at part A specifically and get answers from there. Okay. So let's look at some more solving examples here. Sound good? So we did one with a squared in it. So we probably don't need to do another one of those, right? Probably not. So let's do one that looks like this. Where we have more than one trig function going on here. I would not use an identity here. Think back to your algebra class last year. Does this look familiar? I'm not sure I would want to do that. That's not the familiar that I'm looking for. What was that, Kendall? Yeah, so when I look at this, imagine that y is equal to cosine of x. That means I'd have 2y squared plus y equal to 1, right? What kind of function is this? We spent a lot of time last year talking about these. Yeah. Kind of like that. Yup, that's kind of how this goes. So does anybody remember what this is called? Okay, it's polynomial is what you're thinking for. It is a polynomial. It's a specific kind of polynomial that starts with a Q. You guys are so funny. Not quotient. D. Quadratic. So you remember to solve a quadratic. Thanks there, Sleepy. Okay. So to solve a quadratic, what do we have to do first? So this is a skill from last year. We hopefully kind of remember.
No. You have to get it equal to 0.
It has to be equal to 0. So let's start by subtracting that 1 from both sides.
Wait, so you have to write that? Oh, yeah, practice. That's just practice.
No, I'm gonna. Yeah, we're gonna turn this back into cosines in a second, but we're gonna factor it like this and then put the cosines back in. You can do it with the y's or without.
It's always like that template.
Always like that template.
Like, let's start not template, but let's say the 2y squared plus y.
Well, the 2 is because I had a 2 here,
Yeah.
and the 1 is because I had like a 1 here, and the 1 is because I had like a 1 there. So I used the coefficients from the problem to just basically replace the cosines with y's, right? So it's still the same problem. I just need to, when I'm done factoring, I'll put the cosines back in and take the y's out. If that makes sense, Kendall.
Yeah.
Okay. Just to make it look more familiar to me. Okay? All right. So, does anybody remember the different ways we had to solve a quadratic? You can factor, good. I think that's still part of the factoring process. That is what you're describing. Or the solving by factoring process. What? No, I think it was a good answer. The quadratic formula will always work when it's equal to 0. Good. And those were the two major methods that we used, right? There are some other things that were special case guys that could be quick shortcuts, but you needed like a very special situation to use them. These are two that worked quite frequently and we relied on heavily. Let's use factoring to do this one, because I think that's probably the more familiar, because Hi, Miss Anderson. Wouldn't you already know that you're leaving early? Benny, you should be like, here's a surprise. Okay. All right, so factoring. Remember, there is two kinds of factoring. There was the long way and the short way. When did we have to do the long way?
When there's a number
In front of the squared part. Yeah. So because this number is a 2, we have to use the long method because the leading coefficient is not 1. If the leading coefficient is 1, then we can use the shortcut, and it's a little bit quicker. So what we're going to need is we're going to need the two numbers. I'm going to call those numbers P and Q that multiply to give me A times C, and then also add to give me B. By A, B, and C, what I mean are the coefficients from a standard form quadratic, ax squared plus bx plus c. Yes, we did. So in this case, what is our value for A? And what's our value for C? -1. So that gives me -2. And what's our value for B? 1. So what I need are two numbers that multiply to give me -2, and then also add to give me +1. Which problem do I start working on first? The multiplication problem. So we need to find numbers that multiply to give us -2. What are two numbers that multiply to give us -2? -1 and 2. And those also add to give us 1. So those are the two numbers I need. Okay? If those weren't the two numbers, you'd find a new pair that multiply to give you -2 and then check those. And you'd keep going until you found a pair that worked. Okay. What do I do with those two numbers? In the case that this was the short method, those two answers would tell you exactly how to factor that. In the case of the long method, we have to do a little bit more. So what those two numbers tell us is how to split up that middle term. So that plus y I'm going to rewrite as a -y plus 2y. Notice if I add those back together, I still get 1y. So I haven't really changed anything. I've just rewritten that middle term as two pieces. Is everybody okay there? I then make two groups. And then from the first group, I'm going to take out a greatest common factor. What's the greatest common factor from the first group? Y. Everybody good with that? When I factor that y off, what's left? 2y minus 1. So remember, when I'm factoring it off, I'm dividing. So 2y squared divided by y is just 2y. And then y divided by y is 1. If I look at the second group, what's the greatest common factor in the second group? Well, there's always something. 1 is what it would be. Everybody okay there? So now if I look at this as one piece and that as one piece, I'm going to look for another greatest common factor. What's the greatest common factor between these two? 2y minus 1. Great. And when I factor that off, what's left? Y plus 1. Does that start to ring some bells here? Okay. And at this point, to solve this, what would I do now? I set each of those factors equal to 0. Very good. So the first one we can add 1 and then divide by 2. And the second we can subtract 1 from both sides. Are we done? No. We are not. Why aren't we done? So what were we trying to solve for? We're supposed to be solving for x on the interval 0 to 2 pi. What did we solve for here? Y. So what we're going to need to do is we're going to need to substitute back in cosine x in place of y. Everybody good with that? Feel good there? So to get the x by itself, we'll just do the cosine inverse of both sides. And now we'll go to the unit circle. What are we looking for when we look for x equals cosine inverse of 1/2 on the unit circle? What are we looking for? Excellent. Where the x coordinate is 1/2. What are those two places? It's positive 1/2. Good. And then we'll go to the other one. What are we looking for on the other one? Okay. And where does that happen at? Okay. And just pi. Good. That's okay. Everybody happy with that? That's it. That's our answer now. Okay. So the solving the trig part really boiled down to like a factoring problem from last year, right? And if you remember those, sometimes they're really easy and sometimes they're a little tricky. One thing worth pointing out, just as an aside, what if here instead we got like cosine? Actually, let's just start a new one. Let's do a new one. That's fine. This will be better, rather than doing like some disjointed what if. We have time. Let's just do a straight new one. So what if we wanted to solve this equation for x on the interval 0 to 2 pi? Looks pretty similar to our previous one, right? So let's start the same way, and we'll rewrite this using y's in place of cosine x's. Everybody good with what we did there? What should I be looking to do now? Factor that. Great. What kind of factoring do I have to use on this one? Can I do the short method here? Yes. Why can I do the short method? Excellent, because the leading coefficient is 1. Great. So to factor this, all I need are two numbers that multiply to give me 2, and also add to give me 3. What are those two numbers? That'll add to give me 1, and multiply to give me negative 2. 2 and 1. Everybody agree with that? Okay. So I can now use those two numbers to go straight to my factored form. Everybody okay there? And when I set each piece equal to 0 and solve, I get this. But remember, we're solving for x, not y. So we have to go and make that substitution back that we did in the beginning. So what are those y's going to become? Cosine x's. Everybody's good there? So when then we'll take the cosine inverse of both sides. So what do I get when I do cosine inverse of negative 2? It's not going to be 2 pi. Do you see an x-coordinate that has a negative 2 in it on your unit circle? You don't, right? So either this is a non-unit circle value of cosine, which is possible, and we just have to use our calculator. But go down to the bottom of your unit circle, where we have the cosine inverse information. What's the domain for cosine inverse? Negative 1 to 1. What are we trying to take the cosine inverse of? Negative 2. Is negative 2 in the domain for cosine inverse? What does that tell us then? It's nothing. This is undefined here. So we're getting no answers from that piece. So that part doesn't matter to us anymore. No answers are coming from there. Everybody good with that? Okay, let's worry about the other piece. Cosine inverse of negative 1 we just did. We saw that was negative pi. So that's the only answer for this problem. Okay with that? Let's stop here.